Hello and welcome back to part 3 of our look at chapter 2, dealing with biochemistry. At the end of the second video, we left off looking at and talking about ionic bonds and their role in creating something that we refer to as electrolytes. And in this third video, we are going to be more focused on another type of bonding called covalent bonding. Um, and what is important to remember about covalent bonding is that it is not a joining of two atoms through a give and take of electrons, but it is a joining of two atoms that involve a sharing of electrons. So if we go back to my example of ionic bonding, where maybe your pen runs out of ink, and you raise your hand and you go, "Hey, Young, I need to borrow a pen." And so I walk over and I let you use my pen, but the catch this time, is that you get to use the pen for 2 minutes. And you can write whatever you want. You can do whatever you want with that pen for 2 minutes. But then I get to borrow the pen and use the pen for 2 minutes. And I can do whatever I want with the pen for 2 minutes. And then you get the pen for another 2 minutes. And then I get the pen for 2 minutes. And so there's an equal sharing of the pen. Well, if the pen is the electrons, it is an equal sharing. It is an equal sharing of the electrons. Right? So the electron spends equal time with both atoms that are involved with the bonding. And that's exactly what you are seeing right here. All right, so we have two hydrogen bonds. All right, these are both non-metals. Right? These are both non-metals. Hydrogen here has one electron. It wants one more. Right? Hydrogen here has one electron. It wants one more. And so how it arranges that is it says, all right, between the both of us, we have two electrons. And these two electrons are going to spend some time orbiting over here, and they're going to spend some time orbiting over here, and then come back over here, and then back over here. And so it is a sharing of electrons. Now, depending on the element, sometimes that element has to form multiple covalent bonds with multiple atoms in order to acquire a full valence shell of all participants. What do I mean by that? Well, hydrogen atoms, they form a single bond. Right? They're going to share one pair of electrons, and that gives them a full valence energy shell. But things like oxygen, right? Oxygen has to form two covalent bonds. They have to share two pairs of electrons. Right? Why is that? Well, it is that way because if you remember, oxygen has an atomic number of 8, which means it also has 8 electrons. Right? So oxygen is going to have 2 electrons on that first shell, and then on the second shell, it's going to have 1, 2, 3, 4, 5, 6. Right? It's missing 2 electrons. And so how does it compensate for that? Well, it compensates for that by maybe forming a covalent bond with another oxygen. Because this oxygen is going to have 1, 2, 3, 4, 5, 6 electrons on its outer shell, 2 on the inner. And so if these 2 electrons are shared and these 2 electrons are shared, we now have 1, 2, 3, 4, 5, 6, 7, 8 electrons for over here. And we have 1, 2, 3, 4, 5, 6, 7, 8 electrons circling over here. Right? So now they form 2 double bonds. Right? This is what we call diatomic oxygen or atmospheric oxygen. Nitrogen, for example, nitrogen can form 3 bonds. Why? Because they have 2 on the first, all right, and 5 on the third energy shell for a total of 7 electrons. Right? Well, I'm sorry, for a total of 7. Right? 2 on the first, 5 on the second. Well, it wants another 3. And so it can form bonds. Right? So if we look at nitrogen, for example, here's nitrogen, 1, 2. Right? But it has a total of 7, so we need 1, 2, 3, 4, and 5. Right? Well, what can nitrogen do in order to covalently bond and create 8 electrons? Well, what it can do is it can actually bond with hydrogen, which has 1 electron. And it can bond with hydrogen, which has 1 electron. And it can bond with hydrogen, which has 1 electron. It's sharing 1 pair here, another pair there, and another pair there. 1, 2, 3, 4, 5, 6, 7, 8. This valence shell is now full. And look at what hydrogen does. Hydrogen has 1, it's going to share that one. Hydrogen has 1, it's going to share that one. And so both of these elements get something out of it. This is what we call ammonia, right? Or ammonium, right? NH3. Carbon can form 4 bonds, up to 4 bonds. Why? Because it has an atomic number of 6. And so carbon has 1, 2, 1, 2, 3, and 4. Holy poop. It can make up to 4 bonds. And here's the amazing thing. Carbon can form all single bonds with hydrogen, CH4. That's what we call methane. Or it can form 2 double bonds with oxygen, create CO2, carbon dioxide. Or it can go ahead and create a triple bond and a single bond. What it cannot do is form a quadruple bond. But think about this. Carbon has the ability to form single, double, and triple bonds. It can form 1 double bond and 2 single bonds. It can do 4 single bonds. It can do a triple and a single. It can do 2 double bonds. There is a lot of diversity that is built in. There's a lot of diversity that is built in carbon because it has up to 4 available spaces to engage in creating covalent bonds. All right, so that's exactly what you are seeing right here. Here's carbon, hydrogen, 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 hydrogen. That's what I just got done drawing on the previous page. You've got 4 single bonds that are created. Right? Again, oxygen can create 2 double bonds. Here's 1 bond. Here's the second bond. Right? Nitrogen can do 3 single bonds, or what we call a triple bond. Here's 1, here's 2, and here's 3. The difference here is with an ionic bond, you've got a nonmetal that's joining with a metal through the formation of ions, because remember, one atom is giving away 1 or more electrons, and the other atom is accepting more than 1 or more electrons. It's not an equal sharing of that electron. It is a giving and taking. But with covalent bonds, there is equal sharing. Right? There is equal sharing. In this case, I'm going to give you an example where there is not equal sharing coming up here. But I want you to I want that to sink into you. I want you to sink into this. Carbon has a lot of flexibility in what it can do. It can connect with hydrogen, it can connect with oxygen, it can connect with phosphorus, it can connect with nitrogen. It can connect with any other non-metal that it wants to. Any other non-metal it wants to. It can form double, triple, and single bonds with any other non-metal. That makes it versatile. Right? That makes it very versatile. And you're going to see that time and time again as we start to get into the macromolecules. So don't let that thought get lost. Right? I want you to appreciate the complexity that carbon brings to biochemistry. So I just got done mentioning that sometimes covalent bonds are not engaged in equal sharing, but instead unequal sharing of an electron. In the case of an unequal sharing of an electron, what we see happening is one atom is monopolizing the electrons more than another atom or other atoms. Could be more than one atom. So one atom is getting more time with the electrons, and the other atom or atoms are getting less time with the electrons. And when we do that, we create unequal sharing. We create what we call a polar covalent molecule. You can, rightfully so, add in the term right here. You can add in the word polar covalent molecules, because it is still a covalent bond. There is still a sharing of electrons, but that sharing is not equally split. It's kind of like fighting over a child between two divorced parents. One parent, maybe both parents get the child or the children 2 weekends a month. Great. That's a covalent bond. It's a regular covalent bond. 50-50, equal sharing. But maybe one parent gets the children 3 weekends a month, and the other parent gets the children or the child 1 weekend a month. They're both sharing the child or the children, but they're not sharing the child or children equally. And that's what's happening with our atoms. They're not sharing the electrons equally. And because of that, the electrons spend more time with one atom, which gives that atom a partial negative charge, because the electrons spend more time with it. And because the electrons are spending more time with one atom, the other atoms have a partial positive charge, because they have the children less. They have the electrons less. Right? It's not equal sharing. Take water, for example. Right? H2O. H2O. Right? There's our water molecule. Right? There's our water molecule. Oxygen is larger than the two hydrogens. Oxygen has more protons than what water does. Oxygen has 8 protons. Hydrogen has 1 proton. Hydrogen has 1 proton. And we talked about the fact that opposites attract. We've talked about this idea that opposites attract. Well, are you, ladies, I'm going to pick on you for a second, are you more attracted? Let me preference this. I need you to put your shallow, self-serving, greedy persona on. Right? You're only looking out for yourself, and you're going to be very shallow. No depth to this. Right? We don't care about how charming they are. We don't care how sweet they are. We don't care how good they look in Mark Anthony clothes. We don't care. All right? You got a choice between two guys. One guy is packing 8 figures. He's a millionaire. Right? He's a millionaire. Right? The other guy is a thousandaire. He's just got 1,000. He's just got 1,000. But the other guy, he's got millions. Tens of millions if we're going to stick with 8. An 8-figure bank account as opposed to a 4-figure bank account. Who are you going with? Now, this is your shallow self. This is your self-serving and your greedy self. You're damn right you're going to go with that the person that has 10, 20, 30 million dollars. You're going to go with the 8-figure guy. There's a TikTok in there someplace. I ain't going there, though. You're going to go with the 8-figure guy. The electrons are the shallow females in the class. Usually this is where I have you guys raise your hand in class and identify yourself so that way the guys know who to stay away from. Can't do that here. Just like you're going to go with the 8-figure guy, the electrons are going to go with the atom that has 8 protons. Because there's more positivity there. There's more attraction there. It's what we call electronegativity, where the electrons are going to be attracted to the more positively charged nucleus. And so because oxygen has these 8 protons, the electrons spend more time here, which means they have 10 electrons here, because this one and this one is going here. 10 electrons versus 8 protons, you get yourself a partial positive. It's partial positive because it's not always, partial negative. It's partial negative because those electrons are not always with oxygen. Sometimes those electrons are going to go with the poor, literally the poor hydrogen ions with its 1 proton. As the electron moves further away from the nucleus of the oxygen, it loses its power, it loses its attraction, and hydrogen can go and suck it in. And it can spend some time with hydrogen. But because the majority of the time the electron is not with hydrogen, it's got more protons than electrons. And so therefore, it's a partial positive charge. And so you can see when we have equal sharing of electrons, you get this nice linear delineation of a covalent molecule. That's what you see with carbon dioxide. But when we engage in polar covalent bonding, there's very often a bending effect to the molecule because of the formation of a slightly positive and slightly negative charge. Now, this gets a little bit deeper because water has a slightly positive and a slightly negative end to it, which makes it ideal for being a solvent. It is why ionic compounds dissolve in water, because the partial negative end of the molecule, in this case the oxygen, can be attracted to the positive ion, the cation within the ionic molecule, the sodium. And the partial positive end of water, the hydrogens, can become attracted to the anion of the ionic bonded molecule, the chlorine. And when the water arranges itself around the sodium and the chlorine, their respective attractedness pulls apart the ionic bond so that you end up with an electrolyte. You end up with sodium ions and chloride ions. What happens when you remove the water? What happens when the water evaporates out? Salt crystals reform. The sodium ions and the chloride ions reattach. They join back together again. All right. And so this table here just kind of gives you a visual representation between the three types of bonding that we have discussed. An ionic bond, a polar covalent bond, and a non-polar covalent bond, or what I identified as being just a regular, normal covalent bond. This is a good summary table for you to pay attention to. And then the last slide that we're going to look at here today, right? And that is a hydrogen bond. Now, a hydrogen bond is a special covalent bond. And it is a hydrogen bond that does not hold together atoms, but instead, a hydrogen bond links two molecules together. So, water has this partial positive and this partial negative end. Guess what? The partial negative end of one water molecule, the oxygen, becomes slightly attracted to the partial positive end of another water molecule, the hydrogen, because opposites attract. And the bond that is created from this attraction between the partially negative oxygen molecule of one water molecule and the partially positive hydrogen atom of another water molecule is called a hydrogen bond. It's weak. It's a weak covalent bond because of the partiality of the charge. Sometimes that hydrogen is going to have its electrons. It's not going to be partially positive anymore. Sometimes that oxygen is not going to have those extra electrons, and so it's not going to be partially negative. And this is what allows water to stick to itself. This is what allows water to cling to other surfaces. This is what allows water to freeze, to be a liquid, to be a gas. This is what allows surface tension to exist. This is what allows for polarity, for being a solvent. All of that is predicated within these hydrogen bonds. It's not a sharing of these electrons, and it's not a giving and taking of these electrons, but it is an attraction based on partial negative and partial positive charges that creates this special category of covalent bond that we define as being a hydrogen bond. And we're going to talk more about these guys as we start going through some of the other biomolecules in video 5, starting in video 5. And so with that note, or I should say on that note, I am going to let you kind of digest this. This was a little bit more of a, we're starting to build on this information. So we kind of did some review with ionic bonding, and we kind of took the basic principles of that and applied it to this notion of a covalent bond or a polar covalent bond and its relationship of an ionic bond and a hydrogen bond an ionic bond and a covalent bond, and the characteristics associated with a hydrogen bond. So with that, keep studying, keep reviewing, keep jotting down some information, and you know what I'm going to say. I'll catch you on the flip side.